Alright, so today we're going to be learning about separation of variables as a technique for differential equations and integration and figuring out solutions to differential equations. So what I'm going to do is I'm just going to explain what this process is and show you a couple examples on how to do it, and maybe give you a couple difficult examples so that we can see how different processes work with this technique. I'm Amy. I will be showing you how to do this today, and let's go ahead and get started. So, what do we use separation of variables for? Why can't we just use any other technique that we've learned already thus far? We use separation of variables to solve certain differential equations analytically by finding an equation for the solution curve. And with that, we can consider a separation of variables differential equation to look like this, where it is dy dx equals f of x, so a function of x, times g of y, which is a function of y. So then with this equation, we can definitely see that we need to have either multiplication or division in our overall differential equation in order to be able to do separation of variables. Now, what exactly happens during the steps of this process? How do we do it? Well, first, all x values are moved to one side of the equation while all y values are moved to the other side. That includes our dx and dy, which come from our differential equation notation, dy dx. What we can do is we can multiply dx to the other side, which is usually the easiest method to do. Now, what else can we do? Well, we end up taking the integral of both sides with respect to each of the different variables. So on the left side, if you have dy, that means we're taking with respect to y. And if it's on the right with dx, that means we're taking with respect to x. And then finally, we solve for y after our integral is taken and simplified to obtain the equation for the curve of our solution. And that gets us our answer. However, this technique of integration may not work all the time. So why does this not work? It may be impossible to solve for y. The equation could just be too complicated and you really couldn't solve for y. Another reason is that both integrals may not be possible. They could be integrals which we just don't have a solution for. And then finally, we can also end up missing solutions. A lot of times we have solutions where whenever you work this out with separation of variables, we end up missing a solution which is very evident with other techniques. Alright, so what we're going to do is we're just going to go ahead and jump right into an example. So our example differential equation is dy dx equals xy. And as you can see, we definitely have our multiplication that we're looking for in our differential equation. So we know that we can use separation of variables on it. So let's really do this in steps and really talk through the different levels of what we're supposed to do in each of the steps that we're supposed to take. Alright, so our first step is to separate our variables. So what we can do is we can go ahead and separate by multiplying dx over to the other side. So our first step would be dy equals xy dx, but then we have to move our y to the other side to get it along with the dy. So then you can divide by y, so you can get dy over y equals x dx. And then this can also be written as 1 over y dy equals x dx as well. Alright, so then we can move on to our next step. And our next step is to integrate both sides. So as you can see from the last slide, we did have 1 over y dy equals x dx. So then what we're going to do is we're going to take the integral of both sides, so 1 over y dy equals the integral of x dx, and then we can go ahead and take our integral. Now we know the integral of something that has the -1 power is the natural log of that thing, so you know that the integral of this is equal to the natural log of the absolute value of y, and then that is equal to x squared over 2. And then we can't forget our constants, so we definitely have to go back and write in our constants. So ln of y plus c, and then you have on the other side with your x squared over 2 plus, just say d. This is our other constant that comes out of our integration. And then after that, we can go ahead and jump over to step 3, which is to really combine our constants. So then what we just had was the natural log of the absolute value of y plus c equals x squared over 2 plus d. So then what we can do is we can just combine to the one side of the equation. Since we're going to be solving for y, I usually like to bring it over to the right side, and that's just because it makes it simpler later on. It doesn't really matter if it's like c plus d or anything, because they're just constants. I mean, they could really be anything. So you can just go ahead and write that ln of y equals x squared over 2 plus c, and you can just write it that way. So then you know then that these two constants come together to form this constant. Alright, and then we have our hardest step. So what we're going to do now is we're going to go ahead and solve for y. So then we just knew what our equation was. It was the ln of y equals x squared over 2 plus c. So then what we can go ahead and do is we can raise everything to e to get rid of our natural log, since e to the natural log of anything is that thing. So then you have the absolute value of y equals, and then you took e to the x squared over 2 plus c power. Now, what we do from there is we realize that we have rules with exponents where whenever you multiply terms with the same base, you can also add the exponents. So then you can actually go ahead and separate this, so you have the absolute value of y equals e to the x squared over 2 times e to the c power. Now, e to the c power, what that really is e to any constant. And I mean, with any constant, we know that our e is going to be positive, even if the constant is negative. So what we can go ahead and do is turn this term right here, we can turn this term into a constant. But we know it's a positive constant because, like I said, e to any power, even negative powers, is a positive number. So then we can go ahead and write this as the absolute value of y equals e to the x squared over 2 times c as our constants. That c is out in front, and that is where c is greater than 0 for this step, at least. We're going to write that in pink. C is greater than 0. Alright, so then we have to take care of our absolute value, and we know that our absolute value means that our term on the other side could be both positive or negative, it doesn't matter. So then we definitely know that y equals plus or minus c times e to the x squared over 2 power. And then because of this absolute value, we know that this ends up being where c is greater than 0 and where c is less than 0 as well, because of the absolute value term. Alright, so now I think it's time for an example that's a little bit harder with, instead this time we have trigonometric functions. So what we're going to have is dy dx equals 1 over cosine y. So we're going to just jump into our first step and separate our variables. So what we're going to end up doing is we're going to write cosine y dy, because we multiplied cosine y over the other side, equals 1 dx, because we multiplied our dx over to the other side. And then we can go ahead and jump to our second step where we integrate both sides. So you have the integral of cosine y dy equals the integral of 1 dx. So we know the integral of cosine y dy is definitely sine y plus c. The integral of 1, you add x plus d, and then we can go ahead and combine our constants. Sine y equals x plus c. And then how do we get rid of this sign? Well, what we have to do is we have to take the inverse sign, or the arc sign of it. So then we can say that our y equals sine inverse of x plus c, or we can say that our y equals arc sine of x plus c. What if we did have initial conditions? And so we know that our equation for this problem was arc sine x plus c equals y, right? So then what if we have where y of 0 equals pi over 2? We can go ahead and plug in our values. So you have pi over 2 equals arc sine of 0 plus c. So then you have that pi over 2 equals arc sine of c. So then you would take the sine of each side. So you would have the sine of pi over 2 equals C, and the sine of pi over 2, or the sine of 90 degrees, we know is equal to 1. So then we know that C is equal to 1. So then we can go ahead and say that our solution for this equation with this initial condition is equal to the arc sine of x plus 1 is equal to y.